Okay. Sorry. Where is it? Oh, you know,
Hello? Yeah. Good evening, everybody. Welcome to untoken office for the Ethereum Singapore Meetup. Just let everybody know, you will see one camera there. That is for YouTube Live. So if you want to see yourself, and also can just join the, later I will show the QR code for the YouTube Live. So you will know where we are live broadcasting. A little bit kind of troublesome for this microphone. By the way, same as before, I think maybe some of them you just come to untoken office first time. So in the meetup we just set up by the like a flight aircraft. So the first row always is first class, and then followed by the business class and economy class. So currently, the first class is still free. We don't sell the ticket for the first class. Feel free to join the first class here. And just let you know what's the benefit for first class. Actually, on purpose, we set up like a first class is very comfy chairs here compared with those chairs. So if you want to sit comfortably for the meetup, you can join us here. Yeah, without further ado, first, welcome everybody here. Here, some logistic kind of things to remind everybody. You can get the soft drinks and snacks in the table there, the small round table there. And also the other important thing, so the bathroom. So it's outside the glass door, so the gents and ladies. And then the question is, maybe I asked already, so this is Ethereum Singapore Meetup. So do you know the Ethereum Singapore? Actually, you will find typically 2 Twitter handles. I just talked with one of our Ethereum Singapore member. So find this one. This is the latest one. So don't get confused because you will find 2. And the other thing is let everybody to know. So for Ethereum Singapore 2023, maybe I don't use this one. 2023 on the September 10th and 12th, we have a big conference. So in the National Gallery. So you can follow the Twitter handle to know more details about this big event just before token 24/9. Yeah. And then we have 2 speakers tonight. Just another question. So rare skills, maybe just hands up. So how many people maybe know rare skills? Okay, quite a lot of people know. Good. So we have the rare skills founder here today. So if you don't know, I think everybody know Twitter rebrand to X. Just follow rare skills Twitter handle here. Yeah, then this is my favorite kind of the brand. Yeah, I'm working for imToken. This is the best company in the world. Okay, so join us. Yeah, so if you don't know imToken is here. So we have this kind of very cute, the gold tick. So it's easier for you to find imToken. Yeah, last one before we are coming to the main topic. So like I mentioned, join the Telegram group, because we'll post all the links, YouTube Live, Twitter Live, everything there. And also you will find event photos and also materials later if the speakers are okay to share in the Telegram group here. So maybe this is important for you to join Telegram group. Yeah, the last, Jeffrey. Yeah, Jeffrey is here. Jeffrey is a Rescues founder. And then tonight, Jeffrey will share with us the formula to power the DeFi and also the ZKP. Yeah, thank you, Jeffrey. Over to you. Sorry?
Can I have a water bottle?
Sure.
Water bottle?
Yes, sure. I think we.
All right. Let's make sure. Can you guys hear me okay? Am I coming through? Okay, how about the stream? Is it okay? Yep. Okay, great. Fantastic. Okay, so let's see here. Let me just time myself, make sure that I'm on schedule. I'm going to try to cover 2 sections of topics over the course of my 45 minutes here. So the first section is going to be on DeFi and then ZKP as mentioned. By the way, okay, I guess I should introduce myself. So I'm Jeffrey. I'm the founder of Rare Skills. Rare Skills, you can think of it as a coding bootcamp, but for people who are already senior. So we try to focus on topics that are more rare, hence the name of the company. And prior to this, I led Yahoo's video machine learning department. And that was when I lived in the States. I moved to Indonesia because my wife lives there, and she doesn't want to move to the States. So people think, oh, you're a digital nomad. And I'm more like a digital exile. So I couldn't do machine learning for that company living on the other side of the world. So that's how Rare Skills got started. Okay. Now, who here has heard of Uniswap? Okay, most hands have gone up. How about Compound? How about Aave? Okay, so you guys probably know where I'm going with this then. We're going to talk about how they operate. Who's looked at their code bases by any chance? Maybe on Etherscan or GitHub? Okay, that's totally okay. How about read the white papers or their documentation? How about use the applications, like maybe made a trade on Uniswap or a Compound? Okay, great. So the way I'll introduce these things is, first of all, we need to discuss how do they work in the traditional world in the first place. Because we don't design digital finance, DeFi, the same way we would do like for the New York Stock Exchange or something like that. In the traditional finance, we have an order book. So you guys, the screen is not showing. What happened? Okay, just yell at me if the thing turns off. Apparently my computer keeps going to sleep. So in traditional finance, there's an order book. Okay, I want to buy 100 shares of Apple or something like that, right? So I'll put in an order for 100 shares, and then I have to specify a price, right? I'm going to buy at $10.03. And that's going to, over here we already have some orders for $10.03, so that's just going to augment that. And then over time, there's some buy orders over here, some sell orders over here, and you have an order book. That's when you're placing a limit order, right? So you say, hey, I want to buy at 1003, but there was nobody selling at 1003. The best price at that time was 1004. So if you want to say, hey, I want to make a transaction right now, I just want to take the best price available. You guys know what that's called? Market order, very good. Thanks for participating. So you get priority for one of the swags. So if you say, hey, just buy at the best available price, buy at market, then that will fill your order at this box over here. Okay, nothing complicated. But if you try to do this on the blockchain, then there's going to be some problems. One is there's a lot of transactions in order to run an order book. Because I might submit a buy order for 1002, someone might submit a sell order for 1004. We've both done a transaction and no economic activity has taken place. Now, when you have a highly liquid stock, like on a traditional stock exchange, that's not really a problem. But on a blockchain, you're generating a lot of fees and not accomplishing anything necessarily. So that's not desirable. So you guys have used these applications before, so even if you're using maybe an L2 or something like that, it's still going to add up if there's a lot of transactions. So we want to avoid that. Then there's a more subtle issue about how all of these transactions come about. Liquidity fragmentation. I'm going to say liquidity fragmentation a lot. Who here has heard that term? No, okay, I have to explain liquidity fragmentation. So liquidity means I can easily place buy and sell orders. It's very easy to trade Tesla stock because there's a lot of people buying and selling it. It's really hard to trade real estate because at any given point, there's only so many people interested in a property, and they probably wildly disagree about what the price should be. So that's low liquidity. Now, real estate as a whole is a very active market. There's trillions of dollars in it. But because it's spread out a bunch of properties, the liquidity gets fragmented. And so it's hard for transactions to take place. And when it's harder for transactions to take place, price discovery is harder and capital efficiency goes down. So liquidity fragmentation is very bad in the context of blockchain because there's already less liquidity on the blockchain than there is in traditional finance. Now, where does the liquidity fragmentation come from? Well, that's because we're expressing a preference at a very specific price. So I'm willing to sell at 1004, so at 200 shares, let's say. So now there's only 200 shares if I'm the only seller at that point available. Someone else may say, I'm willing to sell at 1005. And okay, that's great, but for someone who wants to buy at 1004, they only have me as an option. And then for other sellers who have different opinions about what they should be selling at, the order book is very spread out. Now, if there's thousands of sellers, that doesn't become a problem because that will all smooth out. But when we're dealing with less liquid assets, then we get liquidity fragmentation. And you might have heard a wide bid-ask spread. It's another problem. So that happens when, okay, maybe the best buy order is at $10, but the best seller order is at $11. So there's $1 gap where people are not transacting. But there's one thing that we notice about an order book, and it follows the principle of supply and demand. Now, regardless of this fragmentation, the more buy orders there are, on average, should push the price up. And the more sell orders there are, it should push the price down. Now, can we accomplish this behavior without using an order book? And that's where the AMM comes in. So the intuition behind it, I'm not going to, some of you probably already know the formula that I'm going for, but I'm not going to quite get to that point yet. Sorry. Okay, let's just start with a smart contract, which has 2 coins in it. One is a stable coin. You guys know what a stable coin is? Wait, who does not know what a stable coin is? It's okay. You get a free shirt if you don't know what a stable coin is. Okay, great. I'll explain a stable coin. It's an ERC20 token. It's over here. You could, all right. It's a ERC20 token that's backed by like a Singapore dollar or a US dollar in some bank somewhere, and there's an agreement that I can trade this token in for the actual currency and vice versa. Okay, I'm just picking that because it's very easy to conceptualize what the price of that token is. It's always $1. And imagine we have a smart contract. Let's not worry about how the money got in there in the first place. But we have a smart contract which has 1,000 stable coins in it and 500 yellow coins. It doesn't matter. I'm just abstractly picking this. It's probably representing some kind of dog currency. But it's a yellow coin. And we don't actually have a price associated with this here. Now we know that one of these coins is worth $1, right? Just by virtue of the fact that you can trade the bank with it. But this one is a little bit nebulously defined. And in this case, I made a nice example by saying, hey, this is pegged to the US dollar. But what if I picked a coin that is not pegged to a currency? In which case we have 2 coins in here, and there's no statement about the price. Okay, but we want to have a price, right? But there's no price in here. Well, let's apply our intuition. Let's say I want to acquire 5 yellow coins. Okay, so that means if there's currently 500 yellow coins in here, I'm going to try to reduce the supply to 495. So my interaction with the smart contract is going to look like, click my imToken wallet, and I get the 5 coins appear in my wallet. But that's not, we can't just stop there, right? Otherwise, I could just drain the smart contract and take all of the yellow coins out. I have to pay for it. So intuitively, I need to put in stable coins too. Now, how many stable coins do I need to put in order to get my 5 back? Well, let's get to that. But intuitively, if there were almost no yellow coins left, let's say the supply was down here, there were only 5 left. If the supply is low, what does that say about the demand? Not a trick question. Yeah, it's high, right? And when the demand's high, what should that do to the price? Right, exactly. So the more this supply goes down, proportionally more USDC I have to put in. So that's the intuition. When the supply gets scarce, I have to keep putting in bigger and bigger amounts the other coin. And when supply is abundant, then it gets to the point where it's become almost free. So let's turn this into math. This is where we get the, who's heard of xy is equal to k before? Okay, all right, half of you, great. We think of x and y, sorry guys, we x and y as, let's say this was the stable coin, just for example, and this was the yellow coin, arbitrarily picked. Now the nice thing about this incredibly simple formula, actually, right, I don't know how to simplify this any further, is these, the supply will never go to 0, right? Because you can't, k divided by 0 is not defined. So there will always be a price. Now it just means that the price is going to asymptotically get very, very large. So here you can think of this axis being the supply of coin B. Now as the supply becomes smaller and smaller, then the price gets asymptotically big. That's the behavior we're going for. So the question, going back to our previous slide, would be how much of the stable coin do I need to put in to get 5 of the yellow coins back? Well, it's just whatever amount keeps k constant. So this doesn't change. and it will have this property. Okay, that's great. We know how to make a trade. But how did those coins get in there in the first place? And who determined the original K? Yep. We have to put coins in there, right, in the first place. So somebody has to put the coins in there. So what's going to happen to K? If both X and Y increase, then that means K has to increase also, right? So the rules that we have there are you're allowed to increase X and Y, but that might affect K. Now, you might have a rule where the ratio has to stay the same. Might be one rule. Another one is you may add liquidity and change the price. It just depends on how it's programmed. So really, this is at the heart of, let's call it 40% of DeFi. Or I guess Uniswap takes up roughly 30% of the gas on Ethereum or something like that. So as scary as all of that may look, this is really all that's happening. Now, Uniswap v3 with concentrated liquidity is a little bit more complicated, if you're familiar with that. Really just doing that inside of buckets. It's still the same idea. It's not that hard. Okay, so with that in mind, we can move on to interest rates, which is the other application. So if supply and demand drives the price of assets in what should drive the number that determines interest rates? Also not a trick question. I'm sorry? Yeah. So, right. So it's if there's a lot of demand for something, that should cause the price to go up, right? So if there's a lot of demands for loans, people really want to borrow, that should drive the interest rates up, if the supply is fixed. On the other hand, if there is a lot of money in circulation, that's going to push interest rates down. That's what we saw, I think, roughly a year or so ago, right? When money printer go burr, something like that. You guys remember that? So this was a meme roughly when, oh, this is, can we come back? Okay, well, you guys would have seen me putting the joke on the chart at the perfect time, but this thing killed my comedic timing. It's all right. So when there's a lot of money in circulation, then the interest rates go down. Because if I want to borrow, I have a lot of choices. But when money is scarce, then interest rates should go up. So whatever smart contract we program needs to follow this property, otherwise it's going to fall out of equilibrium and people will hack the smart contract. So we're not talking here specifically about the total supply of capital, like there's 120 million Ether in supply or something like that. We're specifically talking about the amount of coins that are in a smart contract in particular. Okay, so we have a smart contract, there's code in it, and lenders put money into it, and so when investors deposit, that causes the supply to go this way, so the chart moves in this direction. When borrowers take the money out, right, that's going to reduce the supply inside of the smart contract. So the money supply goes to the left and interest rates go up. And when the borrower repays, what does that do to the supply? Yep, the supply increases. So now there's more available and the interest rate goes down. So there's really only these four ways that the supply can change. I guess people paying interest rate, I guess, makes the supply go up too, but it's really all it comes down to. And if you read the compound white paper at its core, with a few changes yet, you can think of being one, say there's 100 Ether in a contract, and it's all lent out. So that means interest rates should go super high, because there's nothing left to borrow. On the other hand, if you put 100 Ether into compound, or, well, Ether's not limitable. If you put 100 USDC into compound V3, to be really specific for someone who's going to pick on me, and nobody's borrowing it, you're not going to earn interest. That's kind of different, because if you put money into a bank, you're automatically going to start earning interest right away. But if you put it into a asset pool in a smart contract where nobody's borrowing, you will not earn interest. So that also means that loans will generally be variable, because as you borrow, then other people are going to be borrowing and repaying and supplying liquidity. So you as a borrower are generally going to be paying a variable rate that will change as other people interact with it. Now, Aave has some clever tricks where they can do a stable rate, but you'll obviously be paying a higher stable rate than you will be paying a variable rate. And so in the real world, or at least in traditional finance, if you don't pay a loan, they send the loan sharks after you, right? Well, a blockchain can't do that. I guess maybe when we have cognizant robots, then I guess the blockchain could call a smart contract that will send the robots after you. Startup idea, maybe you can get funding. But realistically, we need over-collateralized loans. Same as when you get a loan against your house. You say, hey, $100,000, I'm going to put my house up as collateral. The bank says, okay, we'll take the house if you don't pay it back. So when let's say you want to borrow 1,000 stablecoin from a smart contract, you need to deposit, say, $1,500 or $2,000 worth of Ether to balance it out. And if you don't pay it back, then there's liquidations where these traders can buy your collateral at a discount. And that's what incentivizes them to keep the protocol solvent. But when it comes down to it, all that's really happening is amount lent over the total supply, which total supply is amount lent plus the amount not lent. So it's pretty cool, right? I've just taught you 80% of what you need to know about DeFi using formulas that frankly cannot be. One is like multiply two numbers together and they're equal to a constant, the other one's just a fraction. It's not complicated. Now, if you look at the code bases, they can actually be a bit scary because there's a lot of details you need to get right. Like at what point do you calculate the interest? Because blockchains cannot keep track of time on their own. They only know something occurs if a transaction took place. How do you know someone's not doing goofy, like, oh, I'm going to liquidate myself, and then maybe I can squeeze some money out of the protocol that way? So you do have to worry about that stuff. And that stuff is non-trivial, which is why we need to hire auditors and stuff like that. But if you can turn your intuition about supply and demand into a formula, then you can architect a DeFi protocol. It's not that hard. Let's get into something a little bit harder. This one. So who's heard of zero-knowledge proofs? Okay. So, well, I guess it means I'll probably have to explain them. So why people are so hyped up about this is because it lets you do some crazy stuff. Like, for example, I can say, you guys know what a hash function is, right? Okay. So if I say I know the preimage, I know a value, when I hash it is going to be 0x5b, whatever the three hash outputs. How would I prove that to you, generally, if I say I know such a hash? Yeah, I would have to give x to you, right? But what if the requirement is I don't give x to you? It's pretty difficult. That was not really, people didn't really have a clear idea how to do it until like 2013. So now people knew it could be done, and but they couldn't figure out how to do it in a way that wasn't way too computationally heavy. Around 2013 is when the researchers figured out here's how we can do it and not be running these exponential time algorithms, basically. And 2013 is very recent, right? So if it feels difficult at first, that's what I tell people when they're running. I'm teaching a class on this right now, and if you don't get it right away, it's okay. The smartest people in the world didn't get it until like 10 years ago. So it's okay. But let's try to be somewhat formal about this. So a proof is a quickly verifiable piece of evidence a computation has been carried out correctly. We need to be very precise about that. Because you Google online, and now I'm a teacher, so I have an incentive to talk crap about other people's tutorials, but it's true. I know something, and I'm going to prove to you that I know it. That's not a very good definition. Like, I'm thinking of a color right now. How's that useful, right? Okay, well, good for you. I'm glad you're able to think, Jeffrey. No, you need to be able to have knowledge of something that's useful. So in this example, this is semi-useful, right? I claim to know that this polynomial has a non-imaginary root, which means it crosses the x-axis at least one point. Okay? And now you could, with being a little bit loose with your terminology, you can say, I know the root of p. So in that way, it becomes a zero-knowledge proof. But it's not arbitrary knowledge. It's knowledge that can be expressed mathematically. Okay, so there's this example that goes around, oh, I'm going to prove to you that I'm over 21 so I can buy drinks. No, that's not a computation. There's no math that you can do that proves you are over 21. You need to have some infrastructure in place where you can say, yes, I have some variable associated with me that's been authenticated by some authority, and I can reveal part of that variable to you, saying it's bigger than a certain value. That you can do, but you can't just have this ID card unless it has some digital signatures inside of it. There's no way you can just say zero knowledge, like I'm thinking of a certain color. Okay, so actually at the end of this talk, who has laptops with them, with the Python interpreter? So if you pay close attention, I will be able to prove to you that I know the root of a different polynomial without telling you what that root is. So if something's not making sense, just raise your hand. So in the last part, it was kind of simple. If you didn't understand that, that's kind of your fault. That was pretty simple. In this part, if you don't understand it, it's my fault, because this is an unusual topic. So feel free to stop me, and you might get a shirt as a result. Let's keep going. First, we have to build up our prerequisites. Okay, we need to talk about clock math. Let's turn this off. Clock math. Who here has heard of this before? Okay, I'll explain it. So, 2 o'clock plus 11 o'clock is 1 o'clock. Makes sense, right? We're using the clock where it turns around at 12, so there's no 13 o'clock. Let's see here. How about 2 o'clock times 5 o'clock is equal to what? 10. Yeah, so this one doesn't wrap around. But what if I multiplied it by 7? What time is it now? Yep, it's 2 again. What if I did 2 raised to the 4th power o'clock? Yep, it's equal to 4. That's right. Okay, this is called modular arithmetic. This is very important in the topic of cryptography. Now, as strange as this is, anything you do in the normal world is true in the modular world. Things stay consistent. I know that might seem a little bit weird. To really get that, you need to study group theory, but it kind of makes sense, right? Intuitively, the things stay consistent. Now, the only thing that's not consistent is if we say 4 o'clock, we don't know the pre-image of that operation. So I say I added 2 numbers together. Well, if you added 2 positive numbers together, you only have a couple choices, 1, 3, 2, 2, and 4, 0. But in clock world, well, I could have done 10 o'clock plus whatever. There's a lot more possibilities. So that is where things start to get a little bit, thank you. Oh, man. That is where things start to get a little bit cryptographic, right? Specifically, there is a property, this is really, really important, so make sure you're following this. Pick a number, pick G, just purely by mathematical convention, and I raise it to A, and I do modulo a sufficiently large prime number where brute forcing becomes difficult, and then I'm going to get a hat. I'm just going to call it a hat. Okay? G, as long as G is relatively prime to it, this works. Now, picking cryptography parameters is a big subject, but I've just picked 2 numbers that the cryptographer is approved of. But these are just normal integers. Okay? The discrete log problem says that this computation is infeasible. So it's easy. This is easy. You can actually do it on Python right now. Warm up. You do it this way. Use Python 3.8 or GAP. Don't do the * mod thing. It's kind of slower. This actually does some optimizations. So you can just pound the keyboard and put some really big numbers into here, and this will answer you in a couple milliseconds. You need Python 3.8, by the way, or it won't work. But this one, your computer, you can brute force it, but then you're going to notice that your time is going to start going start rising very fast. And past around like 200 bits or so worth of P, then you basically can't crack it. Or if you can crack it, you can do a lot of damage in this world. So we believe that it can't be cracked. Now, over here, remember how I said everything that happens in the real world is true in the modular world? Well, we get a nice thing because what is, for those of you who remember your algebra, what's this equal to? Here's some answers. What do we have? Yes, A plus B. Very good. Oh, of course, this is, and if it's true in the real world, it's true in the mod world. This is really, really important. Now, we actually don't, before I go off, I'm about to show you guys some cool stuff. We don't, but before you get any wrong ideas, we don't use this particular trick in zero-knowledge proofs because I actually got this wrong. This needs to be around 2,000 bits to be secure. And this is 0 here. 2,000 is a very large number, and that makes it computationally annoying. So we use elliptic curves, and it also solves another problem that we'll show later. But elliptic curves are strange, and I can't explain them in about 10 minutes. However, elliptic curves have extremely similar properties to doing G to the A mod P. So what we say here is true in an abstract sense for elliptic curves also. Okay? So how is this useful from the context of zero knowledge? Well, I'm now able to do, and this might not be that interesting, but I'm now able to do this. I know A and B such that A plus B is equal to 15. Oh yeah, cool, it's power 14 in 1, bro. Wow. But we need to build up our building blocks piece by piece, okay? But we actually know how to construct this now. Here's how we would do it. Well, we're trying to prove that we know this without giving it away, right? So let's call our little case, or our A equal to, and our B is equal to 15. How do we construct, using what we looked at in the last slide, we construct the formula here? I'm sorry? Uh-huh. Mm-hmm. Yeah, that's right. Here's how you can kind of remember this. Remember, when you're raising a number to a power, G to the A is equal to G times G times G, blah, 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 times G A times. Okay? G to the B is equal to G, or let's put it over here. This will be a little bit more dramatic. G to the B is equal to G times G times G, G B times. Okay. By associativity, I can just, I'm just going to multiply them all together. Now, how many G's do I have? A plus B. Okay. So that, so if we do it in this, maybe I should have picked a smaller number. In fact, I'm going to. So I know two numbers that add up to 5. Let's change this up. A plus B is equal to 5. So A is 2, B is 3. So all I really have to do is just G to the 2 mod P, G to the 3 mod P. Now this becomes something that the other person cannot take the logarithm of. So this is going to become A hat and B hat. Under the hood, remember, because what happens in the real world is true in the logarithm world, in the modular world, we're really just doing G, 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 G 5 times, which is equal to G to the 5. But what the person we're trying to prove to doesn't know is, hey, here's a set of 2 G's, we multiply them together. Here's a set of 3 G's, multiply them together. Now he, the recipient, is just going to multiply them together. He doesn't know how many G's he's holding in each hand. So that will be A hat. So this is the skeptic over here, who we're trying to prove to. So A times B, well, he knows that we're trying to say, hey, I claim I know something that is 5, right? So how does he check that this is equal to 5? What does he put on the right-hand side? Who wants to take a stab at this one? Yes, g to the 5, very good. He's going to put g to the 5, and everything's done mod p. You always have to remember to put this mod p, because you know, like when you take calculus and the teacher always dings you for not putting plus c after doing an integral? It's kind of like that here. But in this case, if you don't put mod p, then your code's not going to work. So it's actually important to put that in. But that's what's going on with addition. Okay. We made a note that addition is really just repeated multiplication. So now we can do something a little bit fancier. We can say 5x is equal to 20. I know x. I know the solution to this. Yeah, obviously you divide both sides by 5. Okay, I know. We're getting there. We need to work our way there. But how could we do this? Well, one not so great way to do it is we encrypt x hat, right? And then the person will say, oh yeah, x hat times x hat times x hat times x hat times x hat. Okay, great, cool, mod p. Is that equal to g to the 20 mod p? Okay, that's fine. But what if 5 is a million? Then that's going to get kind of annoying. What's the shortcut we can use if this constant is very big? So if addition is repeated multiplication, what's repeated multiplication? Yeah. So the person can do x hat raised to the 5 is equal to g to the 20 mod p. If you're taking notes, I'll just give you like 15 seconds to like really mull over it, because this is important before we pull the rabbit out of the hat. If you have a laptop, you can, try it out too. I'm sorry?
The mechanism is more or less state because the fundamentals are there. So you never get it wrong no matter how many times you permutate the model itself, right?
Permuting what? Sorry?
You're permuting using this model itself. So it's really, in other words, no matter how many numbers are put in, it will not affect the structure.
Yes. That's right. I'm actually writing it out just to make it visual. But actually multiplying a number by itself a certain number of times is the same as raising it to a power. Except algorithmically, you can probably take some shortcuts when you're raising to a power versus doing it in a for loop. Okay? So you can imagine, okay, that's cool. If we can do 5x is equal to 20, well, how come we can't do 5x plus 2y is equal to 40? Can we do that? Right? That's not a very big conceptual leap, right? Okay, now we can do something cooler. We can prove we know the answer to a system of equations without giving it away. What's the person going to do? Well, they have to, all additions become, why did the color not change? Strange. Oh. All additions become multiplications, and all multiplications become powers in the modular world. This is going to be rewritten. So the prover, which is us, is going to give us x hat and y hat. And we're going to say x hat raised to the 5th times y hat raised to the 2nd is equal to g to the 40 mod p. Everything is mod p. Cool? All right. Now we're ready to get to the interesting stuff. So turn this off, and I think I jump over here. Or should I do this one first? No. Let's talk about one more thing before I make the jump. Oh, it's already here. Nope. Oh, there. Okay. Before I make the jump, what happens if I want to do 5x squared is equal to 20? Right? X is equal to 2 here. Now, our trick with addition, unfortunately, does not work with multiplication. In fact, if you could make something work with both addition and multiplication efficiently, you probably have either a Fields method or a Turing world. So feel free to explore that. But in this case, we cannot do g to the a times g to the a. This is not equal to g to the a squared. That doesn't work. That's not true. Not true in general. So how do we say, oh, I know the answer to x squared? Well, we can actually just do that. We can say g to the x squared mod n, and then we will call this x squared hat. So we'll just square it on our end. So if we want to jump all the way over here and do this really funky looking polynomial, okay, we have a funky polynomial. I can prove to you that I know the root of this thing, or at least one of them. First, we agree on some parameters. First we agree. Let's just say g in these. So if you're plugging stuff away into your laptop, you can use those values. Now, I've already encrypted these values as 790, 148, and 145. I computed x. I did g to the x mod p. That's 790. I did x squared, g to the x squared mod p. 148. And then I did the same thing over here. Now on your side, remember all additions become multiplications, and all multiplications become powers. So you're going to plug my numbers into here. Wait, sorry. So this is x, right? Originally we had an x over here, so x raised to the 639. This is x squared, and it's going to be raised to the 6th power because there's the coefficient of 6 over here. And we have 775, which is x cubed, raised to the -3. If this really is a root, then in the real world it will be equal to 0. But in the modular world, what's g to the 0? 1, exactly. So if this comes up to 1, you know that I know the root of this polynomial, but you don't know which root I'm using. Thanks for the talk. So if you want to find out more, this is where I show myself. So rareskills.io/zk-bootcamp. And you will actually program a smart contract that uses ZK. So that's the link. Please check it out. Thanks for being a good audience. For the people who are especially good, please treat yourself to this wonderful swag. And we'll have our next speaker up.
Okay, thank you, Jeffrey. Any questions to Jeffrey? Now it's like Q&A time. Let me bring the microphone so people can hear.
Oh yeah, well, I guess if you want to follow up on what's this saying up here. Yeah.
It looks like the verifier function is more complex than the computation itself.
In this case, yes, but when you're doing something really complicated like running a virtual machine or running a hash function, then it's going to be much harder for the prover than the verifier. So one thing we haven't shown here is the bigger the equation, the more x's I have to provide. So that doesn't scale. In the real, how zk-SNARKs actually do it, if you really want to be succinct, you need to do some fancy tricks where you project it into a much smaller space. And then that becomes fast for the verifier and slow for the prover. Which I can't show that trick here. That's unfortunately going to take too long.
Thank you.
Yeah.
Any other
Yeah.
So one thing from today's demonstration is that most of the modules that you just mentioned is very calculus defined.
Very what, sorry?
It's calculus defined. It's based on the foundation of calculus.
Yeah, it's based on the foundation of number theory and high school algebra, yeah.
Right. So where's the expansion from that? Or is it just to expand it through other use cases? Right? Because we haven't really seen much of the use cases other than information of basic tradings and liquidities and such.
Okay. Oh, are you talking about the DeFi thing?
Yeah, correct. So I just want to see if there's any.
Yeah. Oh no, DeFi is very simple. Now, if you do something like pricing options, it can get really hectic, especially when you try to do it without fragmenting liquidity. So, you can check out panoptic.xyz if you really want to see some scary math. Friend of mine. It's not that it is as simple as a solver. A lot of protocols, most protocols are from either Unravel or unravel. So a lot of it is not real engineering. It's very much, we created a new protocol, now let's do some very clever marketing where we get people onboarded, which is not really doing anything that innovative. Maybe it has an incremental improvement here or there. So DeFi math is not, the only tricky parts of DeFi math are pricing options, and I would say trying to do like floating point arithmetic on chain. Like if you try to compute a logarithm when you don't have floats, it's actually a little bit weird, but it's doable.
Thank you.
Yeah.
Any other question?
Yeah. Oh, we have a. Oh, we can. Yeah, we need to get the mic to you. Yeah.
Hey, I have a DeFi question. I don't know if you thought about this before, but if I created a coin and I call it like there's oversupply, right? I created oversupply, and I deposited it as X.
Yep.
And I pair it with stablecoin.
Yep.
That's 500,000.
Yep.
Right? Is there any chance that the price will go lower than, assuming it's
Okay, I don't know that. If you're trying to pair it with a stablecoin, it might just be better to have a smart contract that forcibly trades it at 1-to-1, if that's what you're trying to do.
No, but the price of the token will start rising. But it only start from buying.
Okay, so you start with $100,000 and put the token in. Now, if people buy the token, what that means is if they're currently at 1-to-1, so you have the exact same amount of dollar as the same amount of ERC20, the same of ERC20 of this new coin, right? So the way for the price to go down is for people to sell to the contract, right? Because when they sell to the contract, then the dollar amount decreases. So now less dollar is equal to more of this new coin. So if you can prevent people from selling into the pool, then it won't go below $1.
Yeah, so but total supply in the pool.
I see.
So the only thing is buy. My question is it possible for it to be buy and sure.
Yeah, well, if you can't put, if you know that the dollars cannot be withdrawn and the total supply is in there, then yes, I don't know how you could make the price go below $1. So.
Okay, thanks.
Yeah. Yep. Oh wait, sorry, I think we need to give you the mic for the people on the stream.
So just come in and apologies for asking a stupid question, but just now those equations that you showed, are they integer or floating point problems?
Great question. Everything in ZK is integers done over mod p. You don't ever use floating points. With DeFi, you may or may not use floating. Like when you're presenting a ratio, or sorry, a fraction, it's using integers is annoying for fractions because they might round off unexpectedly. So we would prefer to use some kind of math that represents a decimal point. But in cryptography, we always use integers, specifically modular arithmetic.
So in practice, like what's the number of bits of the integer?
Oh, that for cryptography or for DeFi? So, well, in Uniswap, they use 112 decimal places in binary. So that's roughly how much precision you get. At least that was true in Uniswap v2. I'm not sure about Uniswap v3, to be honest. I think Compound was using around 96 bits of precision to represent the float. This is being recorded. I might be saying something that's totally wrong. You can look at the GitHub and check, but that gives you a rough scale of what they.
96 bits. That means you have to do a double long, right? I guess.
Oh, Solidity doesn't have a notion of double longs or anything like that. It's just how you...
Assuming a long is 64, and so you have to do, and then there's a sign bit in front, so you have to do a double long.
So how DeFi typically does math, this is actually a good question. They don't use, there's not any different kind of data type in, oh, this is not working anymore. Okay, there's not a different kind of number, there's only integer in Solidity. So what people do is they kind of hack the integer, and they say the leftmost 96 bits represent integers, and the rightmost 40 bits represent the fraction. And so we will maintain precision up to that point, and we just program it at a bit level to perform the arithmetic that we want. We don't really have a long or a int or uint or something like that. It is a bit weird. I did find that weird when I was programming in Solidity.
Okay, thank you.
But if you use Rust and a blockchain that uses it, then you'll just be able to use those numbers the way you expect them to. But there's libraries for doing that kind of math, so you don't really have to worry about it.
Nice question. When life contains you want and not just blockchain. The same by use of geometry tool, we can solve a NP problem which is computation is very hard. So are you from the math I want to ask first, are you from a non-computation hard problem to another computation hard problem? That's one thing. Secondly, can we pose like any other NPR problems to edge problems who can solve it?
Okay, yeah, I didn't talk about this slide. So remember, NP might be hard to solve in some cases, but it's always easy to prove. So for example, like the 3-coloring is an example of an NP problem. Now it might be difficult for me to discover the 3-coloring, but I can show you a solution to the 3-coloring. And even when using this, I can prove to you that I know 3-coloring without giving it to you. That doesn't make it easy for me to discover the 3-coloring in the first place. This assumes that we've actually solved the problem, right? I knew the root of the polynomial going into it, just like I would need to know the answer to the 3-coloring.
So like if I'm talking about calculation problem, right? So if someone comes to me with a root of a calculation problem, I cannot look at the root which I am proposing is the reverse.
Oh, you're saying how do I know in the context of the traveling salesman problem that my proposed route is actually the shortest one? Okay, that's actually a really good question, and I spent a good amount of time in my graduate degree discussing that. And unfortunately, there's just no way I can give you a short answer. We'll have to talk afterwards. Yeah.
I was just thinking you can apply it.
No, this doesn't let us, this only gives us proofs. It doesn't help us solve it. It's saying, assuming you've already solved it, you can demonstrate that you solved it and not have to give away the answer. So that's what NP problems and NP problems have in common, right? It's just as easy for you to verify a 3-coloring as it is to verify a list of sorted. That's why it's called non-deterministic polynomial, because it's still polynomial time proving. Now, if we go to a higher thing like p-space, I can't do that, right? Because I can't create a succinct proof for p-space. So I cannot create a zk proof for p-space. Yeah.
So for the proof, in the example of the polynomial equation that we saw, the proof is actually subject to the value, like this, like the combination of pair of prime numbers. So this basically means that when the set of prime numbers changes, and the proof also changes, of course.
Yes.
So the first question is, those set of prime numbers, are they kind of like diverse? Like, so whenever you change to the prime numbers, and then there's different numbers, so there's a different system of the
Yes. So trusted setup. Have you heard that? That's where the prime numbers are determined. So once they're put at the trusted setup stage, they won't change.
So the second question is, what if you want to essentially prove a solution or say polynomial function, but if to
Are you looking for a job by any chance? That's a really fantastic question. So the zero knowledge part actually has a rigorous thing, which means you cannot have any statistical leakage, side channel attacks, anything. It should be, you should be able to generate as many zero knowledge proofs and it should not give anything away, just like with digital signatures are a very limited case of a ZK proof. I can send as many messages as I want and you will not be able to learn my private key if it's properly constructed. So in this case, this is not a zero knowledge proof anyone uses, because there's actually, if you think about it, there's ways you can hack this thing. So this is just to give you an idea how it works. But when we're dealing with real stuff, then you actually need a rigorous proof that no knowledge is leaked.
Okay, any question? Last two? Or no? Okay, thank you, Jeffrey.
All right, thank you. Yeah. rareskills.io/ZKP bootcamp. It's pretty cool.
Yeah, I know 1 hour passed already. Time flies. So again, just for the friends who come late, so the drinks and some snacks are in the small round table. And then again, the bathroom is outside the glass panel. So if you want to go, just feel free. Yeah. Go. Okay, I'm Jeffrey. Yes. Again. Bear with me, since I'm the host, I have been assigned with certain tasks. So there's imToken actually is also actually hiring the tech kind of talents. So actually we have two things we want to highlight here. One is about like we have referral bonus if you refer somebody to imToken. Yeah, referral bonus is here from our HR. Then the other one, so actually we know it's not really dedicated. Sometimes have the job. Is we are catering the talents to see what kind of job are most suitable for talent. So this one actually is a form, so you can tell us what kind of skill and what kind of knowledge you have and what kind of ideal job you are looking for. So then we will just match the talent with the current vacancies. So there are two QR codes. One is actually you can go to the careers.token.in, then the other one is just a Google form. Okay, without further ado, we have the second speaker. So Stephan actually is from imToken. Stephan currently is a Revo lead architect. And then today, Stephan will share with everybody or discuss and also together regarding to how to architecturing the Web3 apps. So Stephan, over to you. So do you have the...
I've got the one. This one's on. All right, are we starting? Hi, good evening, everybody. Sorry, I need to speak slower. I've also got a funny accent, so if you need me to repeat anything, just let me know. So I'll be talking about architecting on Ethereum. I think that there are a lot of considerations that tend to generally go into building applications. Most of those considerations are not necessarily just one thing or the other, but they tend to be things about stuff like specific needs that you might have if you want to build a DeFi application versus what the user expectations are of that application versus what, in some instances, other external factors are. So your architecture tends to have to take into account all of these things, and then you come up with something that tends to find a middle ground that solves or at least covers most of the needs of all the participants, but most importantly, of course, of the business, right? And that's what I'm going to be talking about, business. I should probably have said architecture on Ethereum for business. So I'm Stephan February. You can find details of my profile at February SG. I would suggest that you do not pay close attention to the profile that was shared on the Ethereum Meetup group. In that profile, it looks like I've actually founded 3 or 4 different blockchain-related companies. I think that that is incorrect. I suspect that there was a mix-up with ChatGPT and a zealous marketing intern. So, but yeah, so topics for tonight that I'm going to be covering are token considerations. Like if you're going to build something with the blockchain or with Ethereum in particular, some sort of a token is going to be involved somewhere, and you're going to need to think about the token and what the token is meant to do and how you need to be using it. I'm going to be discussing some general architecture or general architectural considerations, and then specifically I'm going to talk about one specific aspect of application delivery, which is the platform model, which typically is where you have two-sided marketplaces, and then you have a platform in the middle which sort of brings people together. How you should think about building these applications, but specifically, how do we scale them with what we have today on Ethereum? Yeah? All right, so the first item, right, which are token considerations. So tokens, I like to think of them as having features and that there are business constraints that surround the whatever it is that we want to do, right? So first of all, when you think of features, does it have to be fungible, or can it be non-fungible, or does it have to be one or the other? This obviously is the first question, right? And when I say non-fungible token here, I literally don't mean the sort of narrow definition that has made NFTs popular. I'm talking about the idea that one token is either completely interchangeable with the next one, that fungibility, versus whether or not they are completely distinct entities. So think a bus token or a redeemable voucher. Don't think money like Singapore dollars. Yeah. And then, can I split the locked value of the token? So typically a token has something attached to it, and that can be something of value, whether it's a value is represented as an Ethereum or as a number attached to a different token. I'm allowed to split that value because it might be counterintuitive, but you can actually have a fungible token that you can't split the value of. And there might be uses for that, right? So it's not necessarily the case that you have a fungible token that you don't that you have to have this ability to split and merge the token. And the reason I mention that is because it might allow you to think about interesting things and interesting use cases that you might be able to cover with that sort of thing. Does there have to be data attached to the token? And if you're going to attach data, where is the data going to live? Do you want the data to live on chain, or can the data be stored off chain? Do you need some way of giving an attestation of the data that's off chain inside the token or inside the contract that lives on chain, right? So think an off-chain data structure like the Merkleized tree or a Merkle tree, where the root of the Merkle tree is a commitment inside the token or inside the contract rather. Is it transferable peer-to-peer? This is also very important. And the reason I mention this is because it sort of ties into some of the constraints that the issuers have on the right-hand side here. Peer-to-peer transferable, I mean, I can send my Ethereum to somebody else. This new token that I want to come up with that's going to be be used in my business, can I send it? Probably can, because it's the blockchain, it's permissionless, it's trustless, but am I allowed to, right? Quite often you're not allowed to. Can I send a stablecoin, a Singapore stablecoin, peer-to-peer? Without a digital payment license, probably not. Even PayPal is not allowed to do that, right? Person-to-person payments in Singapore, it's not allowed. Is it revocable by the issuer? And now we're talking about permissioned tokens, right? Not everything is permissionless. In business, it is the case that if somebody gives you a voucher for a stay at a hotel, they have all sorts of limitations on that voucher. You can redeem the voucher between this and that date. The voucher is non-transferable. Your name is written on the voucher. Your passport is written on there as well, so you can't transfer it. So if I want to make a digital representation of this voucher for a business, like a hospitality business, then I probably need to think about encoding these same constraints that the business requires into the voucher. And having the ability to revoke the voucher, in other words, rug you from your voucher, yeah. Maybe there is ergonomics built right directly into your token. So, issuer constraints. I mentioned regulatory restrictions before. For example, imToken, right? We're operating as a payments company inside, well, not imToken specifically, but the part of imToken that I work for, which is the Revo network, is actually a regulated payments institution. And we definitely are regulated by the Monetary Authority of Singapore. So we have to think carefully about the things that we do on the blockchain and the things that we are allowed to do. So when you build an application, it's important that you know the landscape, right? There's a lot of stuff that we can do without the permission that is actually not covered by law. But if you want to stay out of jail, I suggest that you know where the lines are and where the boundaries are. And it's okay to push the boundaries now and again, but you step over the line, especially in a place like Singapore, they're gonna come down hard on you, right? Anybody who's lived in Singapore for a while knows just exactly what I'm talking about. So, what about custody, right? If I'm the issuer, I'm issuing this token, what do we do about custody? Am I giving you complete non-custodial? Is the relationship completely non-custodial? In other words, when I give you the token, you have the token. If the token shows up in your wallet, your keys govern what happens to the token. Versus, I give you the token, but the token can only be moved if I agree in the way in which you want to move it. You guys might have recently heard about the Monetary Authority of Singapore publishing a paper called Purpose-Bound Money. So that paper on purpose-bound money is very interesting. So anybody who's interested in these sorts of things, I suggest that you go and read that. It gives very clear guidelines on the types of both financial instruments that are regulated and non-regulated financial instruments, and also sort of gives a framework on how we can think about the idea of wrapping value and then moving that value around. Now, certain types of wrapped value, you're definitely going to have a different custodial relationship than completely permissionless, non-custodial wallets, right? So it's good to think about stuff like that. Security is always a consideration. And there's always a lot of things that we can say about security, right? But definitely something to think about in the context of trying to figure out what we are doing with the tokens that we're building. We want to know, for example, how do we move or transact with these tokens? The digital keys or the private keys and that are used to authorize the movement of these tokens, where are they kept? If we are doing a fully custodial arrangement, in other words, where the business entity maintains custody of the keys allowed to move tokens through the blockchain, then the security of those tokens become very important. Then it becomes important to think about things like hardware security modules, where you basically have the same type of security that you have, actually better maybe even, than what you would have with a hardware wallet. So think enterprise hardware wallet, right? Instead of a small little token that you have, like the imToken wallet, the IM key right back there, instead of a one that you hold in your hand, think a 1U or a 4U rack server that's dedicated to performing massive numbers of computations in a secure manner where your private keys can't be extracted. So just a much larger version of something like the hardware wallets that we get for that you can get for personal use, like with the IM key. Performance and user experience. Performance and user experience are extremely important because from the user's point of view, they need to know whether or not the application is actually working, right? If you're just sitting, if you just sit there with an infinite spinning animation, then the user doesn't know, am I waiting for a confirmation from the blockchain? Am I waiting for something from the application? So even if interaction can't, let's say for example I'm moving a token through the network, even if the confirmation for the token does not happen immediately, and if I know ahead of time as the developer that the confirmation is not going to happen anytime soon, it's better to let the user know, hang on, we've sent it out to the network, you know, and we've all seen this before, right, with our interactions. The tokens basically go out of our wallet, it leaves, but then, you know, it doesn't show up in the place where it is meant to be, but we know, because we've been told by the user interface that it's in the network somewhere, it will pop its head out at some point, and you know to expect that. So setting those expectations for the user are important, but not just setting it for the user, also when you figure out what it is within this larger context of the application that you're building, you can actually structure the entire architecture of your application in such a way that you can give great user experience, especially when you talk about scaling, right? When you give great user experience and you combine it with great security on layer one. Because that's kind of the gold standard, right? But right now, you end up with a situation where we are trying to figure out the scaling solutions for layer two, and quite often you might come up against a scenario where it's not quite clear what am I supposed to do to give good user experience while maintaining both the layer one security, while transacting on layer two, but also, you know, not making the user wait for too long. So, how am I doing for time? Okay. So this is the sort of simplest architecture that you can think of, right? You have a number of users of this business who has a backend server, and that backend server connects directly to the Ethereum network, which means that in practical terms, there will probably be two servers running in the data center or in the cloud, one running your application either on a virtual machine or in a Kubernetes cluster, and another instance running an instance of the Ethereum full node, right? So you have a full node running right next to your application in the data center. And these two communicate, and one of them is on the peer-to-peer network for the Ethereum nodes they communicate on, and the other side of which is your application, that part faces the user and the user interacts with that part. So the user does not actually directly interact with the blockchain themselves through this kind of model, although they can go to a block explorer if you're exposing some part of the application. Technically, for a boomer like me, we don't like something called leaky abstractions. So if your application exposes part of the blockchain, and your application, the thing that the user is interested in has nothing to do with the blockchain, the user shouldn't see it. So that is called a leaky abstraction. So for example, let's say that I've got a ticketing application and the user wants to book a ticket. The user, from the user's point of view, they want to book a ticket, make sure that the ticket is going to be redeemable at the point of redemption at the venue. They don't care about the block explorer or the transaction ID. They don't want to go and check that I'm not running them or anything like that. That is not the case for all applications. If I'm basically trading on a DeFi network, then I want to make sure that things are actually on the up and up, and I want to maybe go and look at the block explorer to see the tokens that are showing up in the place that they are. But for some applications in businesses, think about whether or not you want to leak the blockchain abstraction to the user, or whether or not the user should actually see abstraction be exposed. It might just create confusion, right? So it's something for product owners to also think about. I'm sort of going to progressively get iterate with more, add more bits into the typical architecture, and then work towards sort of the standard high level of what most modern applications on Ethereum would look like. So this one I call the API provider, where you basically have the users interacting with our business through the backend server. Our backend server, we've now realized that, you know what, we're in the business of selling widgets, we're not in the business of running Ethereum nodes. Maybe I shouldn't have to pay for Stephan to sit around looking after the Ethereum node anymore. I don't need a blockchain guy in the company. Sorry, Stephan, maybe go find something useful to do with your life, okay? So Stephan's out of a job, but Stephan is not free to the gainful employment. And Infura, maybe Stephan can go and work for Infura, which is an API provider that runs a lot of blockchain nodes or Ethereum nodes specifically in their backend, and then provide a beautiful API for the still employed developers within backend server company to connect to, right? And those then go through to Ethereum. So instead of the backend server company now running an Ethereum node directly, they basically have all of the stuff, and step over carefully, all of the stuff over here is now outsourced or is purchased as a service from a third party. This is incorrectly labeled processing steps. No, it's correctly labeled processing steps, sorry. Okay, so the reason that I've actually put little yellow tags on the various parts here is because the next slide I actually want to make a point about the various parts of the processing of your interaction between the token, within the context of tokens. If there is some sort of thing that needs to happen where the user either explicitly or implicitly has to interact with the contract that exists on the blockchain, that processing of that interaction that you are brokering for the user goes from step 1, 2, 3, 4. But I don't like drawing it like this. I want to draw it in a different way because I want to make a different point about something else. So I'm tagging it here as step 1, 2, 3, and 4. And then on the next slide, I've drawn it like this, which is 1, 2, 3, 4. 4 is layer 1 Ethereum. 3 is the API service provider we had previously, and then 2 backend and 1 is where the clients are at. And then if you go down, then you see that I call A straight-through processing. Straight-through processing is, again, is a boomer term, something that I know about because, in the 80s it was all the rage. That instead of having to speak, to call up somebody on the phone to do something with a server or system, we do straight through processing. You click a button on the web and it hits the mainframe like that. Amazing. There's no more papers being shuffled. So within our context, straight through processing here just means that the action that the user is trying to take, that you would like to have reflected on layer 1, that it sort of persists all the way through the layers that you have brokered it through to layer 1. More or less unchanged, mostly just sort of handed off and gone all the way through. I'm going to contrast that with a separate one below. I maybe want to say what sort of things A refer to. A would refer typically to something where, remember before I was saying about leaky abstractions. So typically where the user actually cares about what's happening on the blockchain and you need to expose that abstraction of the blockchain to them in some way, that you would want to provide the straight-through processing, the straight-through processing where let's say the user wants to move a token from their wallet to another user's wallet, and they want to observe that on the blockchain, then you provide the straight-through processing, and then the user can see that the tokens have actually moved, right? My NFT is now showing up. The NFT is moved from my wallet to a third-party wallet, and it's actually shown up over there. The user needs to see that, so that's straight through. That is very different from a business wherein you don't need to leak the blockchain abstraction. Very specifically, I mentioned before vouchers, right? But there's a general class of applications or problems like this. Payments is one of them, where the relationship between the person or the person making the payment and the merchant who receives the payment is actually brokered by a third party. And then you have a domain-specific part, which is the payment processing, which deals with accepting money from the customer, and then the money doesn't have to immediately show up in the merchant's account. The token that, even if it's a token that you take from the customer is not going to go look in the blockchain to verify that the money showed up in their account. The merchant is not going to look into the blockchain to go and see whether or not the token has basically moved from the customer to their wallet. Why? Because there is a third party brokering the interaction between them. There's a payment processor, and the reason why there's a payment processor is because this sort of activity is actually regulated. There has to be a trusted third party in the middle. Quite often, in a lot of things that we do generally with the blockchain, we have disintermediated that trust. But there do still exist in the world today use cases where the blockchain, where we can start sort of that middle ground where we are transitioning all parts of the economy to the blockchain, that you still need to have a trusted intermediary, whether it is because of regulatory force or because of just the customers needing still to have this feeling of a trusted relationship. You'd be surprised, but in a lot of businesses, they do not want trustless interactions. They want trusted parties to interact with. And for those especially, the trust exists between the merchant on the one side. And when I talk about the platforms, I'll talk about it again. The trust exists between the merchant and the transaction, and the payment processor. And then there are other parties in there as well. The trust exists between the token holder or the person who wants to make a payment and whoever issued them that token, right? And then there's a whole interaction of brokering that happens in between them. And we're doing amazing things with blockchain to compress and disintermediate a whole bunch of the previously known third parties in that mix, so that it becomes a lot more simple, comes a lot closer to straight-through processing, but it can't be straight-through yet because the governments don't like it. Eventually we'll get there, I'm sure of it. And the way we'll get there is probably through something like what that paper explained with purpose-bound money that MA has published. So we'll get there eventually. It will be the case eventually, I think, that we'll be able to make a direct payment to a merchant with a token that with a non-custodial token that we hold in our wallets. And the government won't care because the infrastructure would all basically be set up in all the contracts will be on-chain and governed, and the right people will make money. Right? So, the thing that I forgot to say at the start was you guys should feel free to interrupt me and ask questions at any point in time. Don't save your questions for the end, because we might actually run out of time. So if you have any questions about this, feel free to ask now. If not, if it's clear... Oh, sorry, so the one part which I didn't mention, which was in B, that domain-specific part that I mentioned sort of on the left-hand side there, are interactions where the business just has to interact with the user. They'll take care of maybe persisting stuff in a delayed settlement to the blockchain in the back end, and that stuff doesn't have to show up on the blockchain immediately either. This has implications for L2 scaling, for example, right? Where you do a roll-up or where you do some sort of layer 2 scaling implementation that does not need to persist to the blockchain immediately. It has to show up eventually, like way eventually sometimes. But as long as the user experience and a trusted relationship between you and the business still exists, then you're okay. So we're getting close to the end now. So I call this slide the L2 platform slide. Think of it as a platform business interacting with a layer 2 scaling solution. And here, so I've got a third slide, and I was thinking about it, and I realized that I should probably have been clear that the solution here is not general layer 2, it's actually specifically layer 2 rollups. So think StarkNet, sorry, does everybody know about the different sort of layer 2 scaling solutions? The rollups versus the, everybody familiar? Yeah, okay. No? Okay, so there are essentially two different types of ways of making the... think about it this way. If you have a storage area where you have a limited ability or a limited throughput where you can actually write to that storage area, and this used to be the case in the old days when you had reel-to-reel tape mechanisms for storing data, right? There is limited throughput for saving stuff. It has massive capacity, but the bandwidth is restricted, so you can't write very efficiently to it. So what typically had to happen is you had to buffer a lot of the stuff, and then wait until everybody went home, and then tonight you run your rail-to-rail, and you do all that processing when nobody is actually on there. So roll-ups, and particularly there are two separate camps in the roll-ups, which are optimistic roll-ups and zero-knowledge roll-ups, which we won't go into, but consider roll-ups as sort of aggregating a bunch of transactions, compressing them into something small, which is zero-knowledge proof, in the case of ZK roll-ups, and then that will fit the bandwidth, and then will sort of occasionally be posted onto layer 1, and you still actually ends up showing there eventually. And the reason why this is interesting is because all of the interactions, the peer-to-peer interactions between you, me, and you and your friends and everybody, all of us, can now happen away from layer 1, where layer 1 fees right now is about $4 on average, thereabouts, US dollars, which is, I don't want everything to happen on layer 1, right? Sort of casual interactions, I don't want to happen on layer 1. I can have it happen for a much smaller fee on off-chain, and that in all places where it happens off-chain with the promise that it will eventually have some sort of a proof of existence on the base chain on layer 1, all of those off-chain interactions are called layer 2 solutions, because they prevent or they alleviate congestion on the base blockchain, essentially, right? So in this diagram, so this is a really high-level diagram, right? So typically, this is the diagram that an architect will show to the business folks. This is not the diagram that the architect will show to the developers. Well, they probably will see this, but there are lots of levels of detail that need to get broken up, and more, where you actually have to expand and go further into detail about exactly how these things actually talk. But at the really, really high level, these components typically exist in all applications, right? Especially when you're interacting, or specifically in the context of building applications for Ethereum. That is that you'll have a roll-up service provider, and the reason for you having a roll-up service provider is similar to why there was the API service provider before. You could probably in your business do the zero-knowledge roll-ups yourself if you had enough data. But for most people, you know, maybe just buy the competence from somebody else who can actually do it for you. And there are a few companies who are actually competing right now with different types of solutions that will actually do this aggregation of everybody's transactions and put them through. So your application will, so again, this is a platform, right? The platform on the right-hand side has some sort of customer, and on the left-hand side is customer. If it is a booking agent for hotels, right? If I'm a travel agent, then I have an inventory of hotels, rooms, and Airbnbs, and all the merchants who actually provide those things. And my application, I expose a fancy web application where I give NFTs to people to entice them to come and book hotel rooms through me. And now I've got to basically coordinate the fact that when somebody shows up at the Airbnb with this NFT, that the host will actually let them in, or maybe the host has one of the newfangled smart doors where I can just actually go with the NFT. The NFT knows it's booked within this particular time slot that has been programmed into the IoT device. I can go up to the door and it'll open for me automatically, and there'll be a little candy waiting for me on my pillow, right? The candy has got nothing to do with the blockchain. All of this, of course, has to happen within the context of something that has to happen on the blockchain. But again, we're doing it now through a layer 2 service provider, or I should say a layer 2 roll-up provider, because I also want to talk about something which by now people are probably thinking of again as boomer tech, right? Nobody talks about state channels anymore, but I kind of like state channels. State channels Does anybody know what state channels are or where they come from? You know what state channels are? Does anybody else? No. Okay, so some of the folks still remember that state channels were actually meant to be a thing. So state channels kind of got supplanted by newer, sexier tech in the roll-up space. If you guys remember that there was supposed to be sort of 64 side chains in the Plasma network, it was supposed to provide scaling. These were supposed to happen on inside state channels. And it hasn't gone completely away, but the energy and the excitement these days are within the roll-up space. The reason I mention state channels is because I don't think state channels are dead, and I don't think they should be completely discarded out of hand. I think state channels still has a place. I think that probably for general use going forward, maybe even for larger businesses or larger applications, you probably want to do roll-ups through a third-party provider. But I think there are lots of smaller use cases where it might actually even be preferable because it might be less expensive and your interactions you broker directly with the blockchain rather than through a third party. Some of the benefits, right? So, okay, that's why I drew the lines. I drew the lines, and maybe this is one of the points I wanted to make about this. Over here, with my L2 integration services, okay, I should say which parts of my application and which are are outside. The orange bits are not my application. The orange bits are things that I purchased from a third party. Everything up there, all of them are actually stuff that I've built myself. Not literally, but that's something that if you're building a business, then you would want to build the bits above, and then same here. But pay attention to the orange lines that I've drawn in here, because I want to make a point about those. The orange lines here with state channels, because of the way that state channels work, you actually as not just the business, but also as the participants on the customer side, or the customer side, but let's say the customers on the left and the customers on the right. All of these participants actually have the capability of directly interacting with the blockchain as well, as part of this entire ecosystem or part of the greater solution that the state channel provides. And they don't have to do it consistently, constantly, or all the time, but I do like the security that you can then move to potentially non-custodial relationships or other sort of interesting aggregate relationships of where you have maybe aggregate state channel hubs that with security. It doesn't have to be a third party that you pay. It could just be you and a couple of your mates who basically commit money to open up a channel to a particular state channel as a contract, and you all interact through that one. And you have some way, a trusted relationship between you and your mates where you're all committing to that. I don't know, but the possibilities are endless, right? And the API service provider that I put at the bottom here, the reason you don't see layer 1 is because this is kind of implicit, right? When I send a transaction through Infura can't do anything with my transaction except send it on to the layer 1 node and maybe charge me a fee for the privilege of sending it through them. As opposed to this here, where you kind of have to trust that the layer 2 rollup guy is going to do the job, and then they're going to charge you a fee for the job that they've done, and then eventually your rollup will show up on the blockchain. I've been quoted 24 hours, maybe, preferably between 24 to 48 hours. You'll see it, and if it doesn't, then to see whether or not it has or not. We're not going to send you a response, right? So I like state channels, but these are very sexy because the math is sexy, right? But I like state channels. They're a bit boomer, but they kind of work for specific use cases. Yeah. Any questions? That's pretty much about what I wanted to say about that. Any questions? Sure. Yeah.
So for layer, if let's say you want your layer 1 contract actually stop. Okay. So
So we have YouTube Live.
Yeah.
Cool. What happened? Let me try again. I think it's
Go for it. That's okay, you go.
Oh my god. Oh my god.
I don't know if it's you or me.
One more time?
Okay. So, my question is regarding the layer 2, but in this setting, if let's say you want to keep updating information from layer 1 to the backend, you kind of should use a layer 2, right? What should the architecture be?
In B, scenario B,
It's kind of scenario C, right? Because there's no layer 2 here in this. Take it that the back end is equivalent to layer 2, then what should we be?
oh, sorry, maybe I didn't make that clear. So I was being a little bit abstract when I was talking about the solution in B. Either of these two can actually be using a, well, actually layer 1 is definitely all the way through to layer 1. A, and then B is the delayed settlement. It was kind of implied on my part. I didn't draw it in clearly enough. I'll update the slide. But the implication there is that within that delayed settlement time, and I mentioned the 24 to 48 hours, right? You can pretty much do whatever you do, whatever you need to. You can stick a layer 2 solution in there, or anything else.
Let's say it's a smart contract, and a few months later you want to update stuff.
Right.
You should you shouldn't use a layer 1 to update it, right? You should use layer 2 and then push into layer 1. So how is that architecture done?
Okay, so it is pretty much still the same. It would be either this or this. Typically what has to happen in your case, in the case that you mentioned, which is actually a really good example as well, because what happens in the intervening time, let's say you want to keep 1 month's worth of state transitions or state updates. All of that has to basically be done here. You have to store it in your database. You have to make sure that you record each of the state transitions depending on what sort of commitment you're going to make to layer 1 eventually. And in the case of a really long delay, I don't know if you can delay something like StarkNet. No, because StarkNet decides when they roll up their commitments, and so does Optimism. You don't get to decide. When you send your transaction, it goes through. The only time where you actually have the control on whether or not the commitment is made to the blockchain is with the state channel. And if you are in control of the state channel and all the parties who are participating in it agree. So if you have that long of a time for you to collect state transitions, then I think that state channels probably are the way to go with it if they fit your use case. But generally, I don't know that you could always buffer your transactions off chain, but that is risky with StarkNet or with the other layer 2 solutions, because buffering off chain means that you run the risk of the state on layer 1 if you're not careful, you won't accurately reflect what the eventual state on layer 1 actually needs to be. Because the sequence of the contracts that need to be committed might be non-deterministic when you broadcast them, and if they're not in sequence, then some of them might not persist. It's a bit risky. Any other questions? Sure. Yeah, there are a couple of companies. There is one called Nitro, Go Nitro. They have a pretty good one. There was another one that I found that. So I should say, right, that I haven't myself. I have to find my browser now. I haven't found. Let me see. Okay. sorry, I'm going to move this off because I might accidentally open up nuclear codes. So, which you're not allowed to see. Let me see quickly. You know my private keys? I'm trying to remember now the one that I found. Perun. I'm terrible with remembering names. So there is Perun, who still seem like they're alive, and then there is the Go Nitro implementation, which had a GitHub commitment just 3 days ago, because that's normally how I tell whether or not a project is dead or alive. And then Perun network. For some reason I can't find a good link. But Perun, they still look like they're pretty much alive. Go Nitro was from a company, I think they're called, I can't remember their name now. Or rather, Go Nitro is basically the Go implementation of the network. But my research basically sort of suggests that Perun and one or two others are the ones to look at right now. But there are a few. There are a few out there. Any other questions? Yeah. And then over there. So we have 2 questions. Sorry, the mic is back there. We'll come back to you. A vulnerability in which wallet, sorry? Oh, most of the wallets. There was, I don't know if it is, so I didn't read the article that you're referring to today morning. I do know that last week there was a little bit of a scare around a very specific multi-party computation involving Paleo curves, which is basically sort of groups of people doing multi-signatures for particular types of wallets. And then also there was a bit of research that came out around a vulnerability that exists within elliptic curve DSA that specifically, under a very specific circumstance, if you have 2 signatures over the hash, and one of those signatures is a faulty signature, that it becomes possible to reveal the private key with just the public key, the message, and in the signatures. But those are but both of those vulnerabilities are a bit esoteric and not the sort of thing that most people need to worry about. I don't know if anybody else knows anything about the news that dropped today morning that you're referring to. I don't know, did you read them in the newspaper or online? In the Straits Times this morning, then it was probably last week's news. It's probably referring to these vulnerabilities that were found in these wallets, or rather within this very specific area of cryptographic signatures, which tend to be used by people like BitGo or the custodial services tend to have multi-signature wallets that they protect with. And a lot of them actually use this particular way of doing the ECTSA. I think it's Paleo signatures. And there is.
I know which one is that. I know it's the one that is closed by Fireblocks this moment. The big forge vulnerability.
Did Fireblocks do another one? Because last week's one was by Fireblocks. Is it the same one?
2 days ago.
For 2 days. Sorry, time works weirdly in my head. But yeah, sure, maybe on the weekend. Yeah.
Thank you for the talks. You mentioned about the DM application layer 1, layer 2, but we have some game options for actually working on multi-chain applications. So how do you think about the differences between using layer 2 for scalability or and using different chains for not only about scalability but also about tiling different communities or different regions? So
Yeah.
how the architecture of multi-chains look like?
I think that's actually a fascinating question, and a lot of people have proposed this, right? Which is, as opposed to doing a side chain, maybe just use a fast blockchain to support the scaling of a slow blockchain, right? That's kind of what folks are saying. There are two interesting things that is notable and noteworthy here. The one is the economics, right? So it starts to become about economics and about who absorbs economic value from whom in this scenario. Let's put aside the economic considerations for the time and just say that we actually want to do this sort of scaling. I think it's a brilliant idea. However, the sorts of things that need to happen are we need to have the capabilities on both chains that you would like to integrate to do certain cryptographic operations, or at least certain types of operations that allow for cross-chain swaps, for example. So HTLCs, hash time locked contracts. If you guys don't know, maybe ask me afterwards. I can explain what a hash time locked contract is. But there are things like HTLCs which allow you to essentially do atomic swaps cross-chain, but both chains need to have support for the notion of there needs to be certain primitives supported on the chain so that they can participate in what is essentially a multi-party computation through the HTLC, because you need to do stuff like both parties need to lock funds on each of their chains, and then they need to, and those funds need to be locked with a time delay. If you can't do a time delayed lock on your chain, then you're kind of out of luck. Bitcoin BTC has a particularly nasty feature which makes it difficult, which is what I like to call rug by fee. They call it a replace by fee, but it means that you can rug the transaction after you've broadcasted by posting a new transaction with a higher fee attached to it, right? So if you're participating in an if you're participating in a HTLC with BTC, for example, with somebody on BTC, then you would want to be careful that you don't get rugged. And while the HTLC exchange kind of has it built into the exchange, the atomic swap, that you can't, or the cross-chain atomic swap, I should say. That reminds me, you basically want to be careful with that. I do want to mention this company that I worked with these guys in a previously. I'm not seeing anything showing up over there. But these guys have done great work in building out infrastructure. Is it CoBlocks or CoBlocks? Roblox, really? Come on. Of course, I'm going to find them now. I can find everything, including a paper on the ACM. But there is a company, CoBlocks, that I worked with the developers like maybe in 2019, and they have since done some really good work with actually doing cross-chain atomic swaps, which is a key component of cross-chain scalability. If you want to leverage another scale to scale one, then you need to figure out a way to do atomic swaps of tokens across them in some way. Yeah. In that case, maybe, I don't know, you need to figure out a way, from an architectural standpoint, because maybe I didn't answer your question right. From an architectural standpoint, your infrastructure will probably end up becoming interesting, to say the least, because you now need infrastructure that you probably can't really outsource anymore for your end of the atomic swap, because you really want to. Because consider it this way, right? If I'm trying to perform an if I'm trying to do a HTLC with somebody on another chain, let me bring this in again. If I'm trying to do a HTLC with somebody on some other chain, and I have to traverse through a rollup provider onto the network, I don't think that's going to work. We are probably going to have to go back to this diagram here, right? Where you're probably going to have to do something directly on the Ethereum network, or perhaps this way, where you have a smart contract on Ethereum, which both parties transact through as the Ethereum side of the HTLC, and then on the other chain, if it's UTXO chain, for example, because these tend to be the interesting things, right? How do you go from a BTC to an Ethereum cross-chain atomic swap? Because one is UTXO and the one is account-based. Which co-blocks actually managed to work out and figure out, and they've got code published for it as well. It actually works quite well. But I don't think anybody wants to scale Ethereum with BTC. So, yeah. Any other questions? Nope. All right, then I think we can draw a line under it there. Thank you very much. I appreciate your time.